Good afternoon, everyone. I hope you're enjoying the PX4 Summit as much as I am. And it's great to be here, and I'm so glad we were able to fly all the way from Abu Dhabi and get here. So now kind of getting over the jet lag as well, right? So my name is Tintu Jose. I'm the director at Secure Systems Research Center, and I have here Govind with me, who is our lead engineer at Secure Systems Research Center at TII. Today I'm going to be talking about the secure, resilient, and safer PX4 Autopilot system using the RISC-V processor and SoC security capabilities. So before we get started, I just wanted to give you an overall agenda. Of course, we'll be introducing our company, TII, and of course our department, Secure Systems Research Center. And Govind here, he would be going over the PX4 security work that we have done in 2021, which is last year, and also the current work that we are doing. And we'll also be having a demo video at the end. So, quick introduction. Who are we? We are TII, Technology Innovation Institute. We exist to help create a better world. We develop the most advanced technological innovations designed to benefit the society. We are part of Abu Dhabi government's Advanced Technology Research Council, which oversees the technology research in the Emirate. Now, you can see a lot of research centers here. We have 10 research centers currently, and we are one among them, which is the Secure Systems Research Center, and we have our Artificial Intelligence Cross-Center Unit. So now just to deep dive on Secure Systems Research Center. I know I keep saying Secure Systems Research Center, also known as SSRC, so I'll use the short form as SSRC. What we do is we develop end-to-end security and resilience for cyber, physical, and autonomous systems, including the platforms, the cloud infrastructure, and communications. Now, just to deep dive into the Secure Systems Research Center, we have 3 different teams in there. There is our Secure Common Technologies team, there is our Secure Mesh Communications team, and then there is our Secure Autonomous team. So what does the Secure Common Technologies do? They offer end-to-end, modular, scalable, secure, and resilient reference architecture for key components like the operating system, the hypervisor, and app virtualization that is applicable to a wide variety of communication and compute devices like the phones, the drones, laptops, etc. As for secure mesh communication, that team actually builds secure, resilient, and infrastructure-less or mesh communications for machines to machines and humans to human exchanges. As for secure autonomous team, we actually develop an end-to-end security and resilience solution for all the key components from the ground up, so from the silicon to the cloud for unmanned aerial systems, which includes the flight controller, the mission computer, the flight, and the mission operation. Our goal is to really make the PX4 NuttX-based system secure. We have been working on it from the last year, and we have put in all the plumbing, and so we are able to achieve it. Our roadmap is also to ensure that we are resistant to attacks, and we have this partially working in our SWAM mode right now. This is a deep dive into the secure autonomous team. This is our architecture. This gives you a snapshot of what we want to achieve. So we have our cloud communications, we have our mesh communication that exists between the folk drones, the edge drones, and our mobile command center by the bus there. And this way we make sure that we have a fully connected working environment at all times. So now I'll actually pass it over to Govind, who is going to give you a recap of what we have done and what is our current ongoing work. Over to you, Govind.
Yeah, sure. Hi, everyone. Thank you, Tintu.
Okay.
Hi, everyone. So my name is Govind. I'm working in Secure System Research Center as lead software engineer. And today I'll be talking about the work we are doing in the PX4 stack, for our secure autonomous flight computing platform, and mainly focusing security and resilience aspects. So I'll be mainly focusing on the security and resilience. So let me start with a quick recap what we did in 2021. So in 2021, we basically added in security and resilience point of view, we added, enhanced the PX4 flight software stack in following 3 areas. So first area is verified boot. Second area is we enabled the protected build. So it's slightly different than the native protected build. And the third one is we added the generic crypto interfaces, which was missing. And we enabled a use case that is SD card lock encryption in the very basic use case. So in verified boot, what we did is basically in the PX4 bootloader, we added the signature verification support, and apart from that, embedding the public key in the bootloader. And in the PX4 firmware side, we added the table of content structure, and which has the signature descriptor and all the associated fields so that we can have the complete signed boot support. So this feature is landed upstream. So there has been a lot of review and refactoring, and finally it landed last month. And the second feature is the protected build. In this protected build, what we did is based on the trust level, we basically modularized or like partition different PX4 components. So like more secure components are basically kept in the kernel space, and the lesser privileged or which has the attack surfaces, those are kept in the user space. So for this, what we did is, the NuttX is designed in such a way that just tweaking the linker script, we are able to put the modules from user space to kernel space. However, for the inter-module communication, the micro URB is completely put into the kernel, and we created a shim layer using the ioctl interfaces. We enabled the inter-module communication. So with this architecture, we are in a way minimizing the attack surfaces, and like some of the new components like the crypto and all, we are able to compile within kernel space, or any module which is directly interacting with the low-level driver and all, we are able to compile within kernel. And like less secure component like mavlink, which has directly the radio attack interface, so we are able to put it in the user space. So this is also available in the, it is also merged in, it's upstreamed, it's available in the mainline. So if anyone want to use this feature, he can basically check those PRs and enable in their code base. The third one is the crypto interface. So for the crypto interface point of view, we defined a generic crypto interface, and in the crypto backend, to start with, we enabled the software crypto. So in the software crypto, we have monocipher or libtomcrypt library. So we enabled so that we can have a basic use case of SD card encryption, the logs we are putting, so we are able to encrypt. So this is also adding one security primitive, right? So all of these features are in detail discussed by our lead software architect, who is Jukka Lahtinen. So you might have seen a lot of PRs from him, and he is very active in PX4 community, and he's also technical lead for there is security foundation. So please feel free to contact him over the PX4's Slack or in the community forum, or he can help with if you have any queries on these aspects. So this is the quick recap what we did on 2021. So let's move on what we are doing and what we did in last year. So the ongoing work. So first of all, I want to introduce you with our next generation flight computing platform. So what we did is we basically created our own custom flight computing platform based out of RISC-V system on chip. So RISC-V, and I think everyone is now familiar because of open ISA, the whole industry wide it's getting adopted. Big companies are also slowly migrating from COTS M to RISC-V because of the open ISA, and also it is allowing you to customize, right? You can create your own SOC, you can put your own SOC capability in terms of security, and you can tape out. So that's why industry trend is moving towards RISC-V. That is the reason we adopted to RISC-V. So if you see, to start in the first generation of platform, what we are doing is we used off-the-shelf commercial RISC-V SoC from Aris Embedded, which is using the microchip PolarFire, which is quad-core U55 based RISC-V platform. And we designed our own carrier board, which is FMU V5X standard compatible connectors. And in terms of performance in memory, we have significant improvement when we compare with STM32F or STM32H based PIC-SOC. But again, someone can have a rationale like why you want to have just for flight computing stack quad core. So I'll come to that, how we are migrating from external mission computer and running complete mission computer and the secure OS and the PX4 in the same system. So I'll talk about it. So also we have the sensor board with triple redundancy. So from the software point of view, what we did is the first thing in the ecosystem. So we are the enabler in the RISC-V in NuttX. So we enabled the RISC-V support at least in the application processor U54 target support in the NuttX community. And the security hardened features we added, which I already talked about, the protected bill, crypto interfaces, and yeah, sure. So let me move on. So this is the quick comparison of the STM32 like PXOC 5X versus our first generation, the second generation flight computing platform. So if you see that SOC point of view, STM32, and we have the RISC-V based quad core CPU performance wise, so there is a significant improvement. So we have FPGA integrated in the subsystem. So we want to do any extra workload or any other thing, machine learning aspects, we can explore it in the FPGA. And from the connectivity point of view, so we are supporting the long-range Wi-Fi connectivity for mesh kind of thing, which Tintu explained in the use case, and we are using like long-range Wi-Fi over PCI using Doodle Lab, which is Qualcomm-based, and QCA 9880, because in the upstream kernel, they are supporting the 11S mesh, so we are leveraging that. And apart from that, security point of view, if we compare, in the first generation, we have verified boot, cryptolib, a protected build. And in the second generation, we want to exploit all of the SOC capabilities, be it root of trust, be it hardware accelerated cryptography, anti-tamper protection, and the AMP mode. So in the AMP mode, what we are doing is, since it's quad core, so we are, from the bootloader, we plan to start in one core in the PX4 stack, another core, the secure OS, which we are using SEL4 microkernel, and the remaining two cores will be having the Linux, which will be running the mission computer stack. So plus we have the mesh support in the both generation. So from the work point of view, so our work is broadly categorized in three categories. One is NuttX, then PX4, and the generic. In the generic category, what we are doing is all the platform aspect, like board support package aspects, which is related to RISC-V. And so we are enabling in the generic platform infra for U55 RISC-V SOC. And then we are customizing bootloader so that we can run the AMP mode, and we can run three different execution contexts, be it PX4 or like SEL4, which is secure software stack, and the high-level operating system like Linux, build root, or like any hardened OS. In the NuttX, what currently we are focusing on enabling the full lightweight process model, since we want to use the MMU, because if you see STM32, it can only give you the MPU kind of protection, right? However, with RISC-V, we can use the virtual MMU, and we can enable 39-bit virtual address space. We have PMP, IOPMP, so physical memory we can protect, IOPMP, IOs we can protect, and with AMP mode, we can statically partition between these different contexts, and we can have a better kind of resilient and the secure system. Then we are enabling the POSIX shared memory interface, because natively we have a mountable FS-based SSM. So we are going to message queue. So we are exploring, and there is already a thread in the community open where we're discussing like how to implement the message queue based SSM POSIX compliant, so that we are in a Linux compatible way. Apart from that, we are in a path of designing our own RISC-V based system on chip. So this is also a work in progress. It is in pre-silicon stage, and we want to slowly migrate to our own custom SOC and get rid of the off-the-shelf commercial SOC. So then on the PX4 side, we are basically making sure the PX4 modules can run as a separate process. So this is also like exploiting the MMU capability. So also the improved version of micro ORB library, so that we can use the, for IPC better way, we can use the semaphore and the signaling mechanism. So this is also one work in progress. A early prototype is existing in the downstream code base, but which will be slowly, we'll be planning to upstream. So with this, I want to hand over to Tintu for the demo.
Thank you, Govind. So now that you have heard the theory of it, of course, you would want to see things in action, right? So I suppose most of you have seen this in our booth already. What we have here is, if I can play this. Okay. So what we have here is a simple demo which showcases our secure flight controller that he has already described. We have our own ground control software over here that works over the cloud, so we can sit anywhere in the world and control the drones. Here, what you see is there's 2 drones flying in the same mission. And the waypoints are provided to them in the ground control software, but the assignments of the waypoints are done by our own mission engine, and this is this is done on the drone and shared over the mesh from the leader drone to the other drones. Now, this kind of ends our demo, but we have done other demos related to security capabilities and what we have achieved, and feel free to drop by our booth. We'll be there. Also, our colleague Kesuk, he's also present there. So this kind of brings an end to our presentation, and I would like to thank you all for your time. And for any of the PX4 related questions, please contact Jukka Lehtinen. That's his email address. I'm just giving that away. And also he's available on the PX4 community as well as on the PX4 Slack group. Thank you.